Jai Hind everyone. Today I am going to just deliver the lecture of the subject compiler design, and now I am taking the lecture of 5th unit, that is code optimization phase. You all are aware that the compilation process is divided into different phases, and all the different phases, the backend phase are basically code optimization and code generation, because we are just converting the code, the source code, into target code, and the process will be started after particular changing the code will be from this code optimization phase. Sometimes we will call it middle layer because it is an optional phase. Might be if you are putting your best effort during lexical analysis to intermediate code generation, and might be you will be just changing all the code and tried out to inculcate all the optimization during all 4 phases. Then might be it is not needed that you will use that code optimization phase. But still, if some particular optimization requirement will be left over during these 4 phases, then we have to adhere this code optimization phase for this part. So now I am going to discuss the optimization of basic block. You know that firstly what we have to do, whatever intermediate code we have generated during previous phase of the program or source code, what we have to do, we have to convert it into the basic blocks. And you know that all the basic blocks is divided into on the basis of leaders, and these leaders are the some kind of a statement through which you can just divide the basic block which contains some of the particular program part which is in connection of a particular part. So you can divide this part so that you will just separate the particular your looping construct or any conditional statement, because a lot of statement is adhere in that particular part. So whenever we have just converted it in the basic block, that is the first step for that. After that, what we are doing, we have to optimize all the blocks by applying these code optimization techniques. So what we are using, different structures, preserving transformations can be implemented by construction of DAGs of basic block. So directed acyclic graph is one kind of structure through which we can optimize the basic block. And the basic structure that is used for this optimization of basic block for DAG is triples, because we are using triples because number of optimizations we will done in this DAG representation. So triples is the best structure. Optimized triples are the best structure which is used to optimize this basic blocks. So if you are just try to understand the DAG structure, so DAG is a pictorial representation of a basic blocks in which there should be a tree, that is directed acyclic graph. There should be no cycle for that. So there are leaves, interior nodes and root. So interior nodes are just labeled by an operator symbol. Might be interior nodes will use some intermediate results, that variables are associated with the interior nodes. Leaves are labeled with the raw particular data, either it is kind of a variable or any constant value. Then nodes optionally have a list of labels that I have already told you. Might be some identifiers, because if you are putting x equals to y plus z, so you know that with plus this additional identifier will be used, and y and z are the basic. So this is kind of a structure of DAG. Then if you are finding the significance of edges, then edge relates operand to the operator. Interior nodes are operator basically. So these are edges. That is relates that either it is left side or right side, or whatever the requirement of calculation is that. The one important thing is that interior nodes represent computed value. Every time you are getting the value at intermediate interior nodes. So internal nodes are the basically putting that value, and whatever value that would be calculated and just raised by that interior value, internal value or interior value, interior node. Those particular values analysis is basically optimize the basic block. So we will see in next particular PPTs how we can just optimize these basic blocks by using this directed acyclic graph representation. So this is the example of DAG. Okay. Suppose we are putting this T1 equals to 4 into I. The important thing is what? We cannot duplicate any particular of a statement in the DAG. In the DAG, whatever information is given multiple times, you will put up in one time, so that we will find that what kind of optimization is required by using DAG. So like this example, T1 equals to 4 into I, T3 equals to 4 into I. There are two particular variables are given. So if you want to design the DAG for these two separate entities for different programs, then it will be okay. But for one program, what will happen? T1 and T3 will be used on the same place. T1 and T3 will be used on same place. And here what we find? The important analysis is there that the T3 and T1 definitely compute the same value. So what we will do for optimization, this is called local common subexpression value, because there is two common variable, they just compute the 4 into I. So either we need these two values, or we may remove any of them according to the whole program structure. Might be T1 is used multiple times, T3 is used for one time, might be we will remove T3, might be T3 will use multiple times, T1 is used one time. So we will just exchange these particular values and we will just improve. We had improved the particular code by using this. So like if you are putting any conditional structure, if I is less or equals to 20, how we can draw the directed acyclic graph. So less and equals to, that is kind of operator. L1 is the particular targeted statement where this particular value is going to. So this is the kind of representation of that. So if you are seeing this particular structure, how we can draw this DAG? So you will see that T2 equals to T1 plus T3. So star and plus both are represented that value, because T1 plus T3 is used for T2 also. So we can use this T1 plus T3. Okay, T1 and T3 is given here. Then we have used this plus, both are come here and T2 is there. So T2 is what doing? T1 plus T3. So this is kind of a structure. So there is no duplicacy when we are going to design this directed acyclic graph. Now construction of DAG. How we can construct this DAG? So there is a method and algorithm that is used for creating DAGs, so that initially when we design the DAG, no duplication of particular statement which is multiple time used. So that duplicacy will remove after when you just draw the DAG from given triples. Okay. So what is the input? We require basic blocks. So what we have to do, whatever program fragment is given, firstly we have to convert it into basic block, because basic block will be optimized by code optimization techniques. So DAG, loop optimization, data flow analysis, everywhere. If we want to perform this code optimization, naturally, firstly we have to convert the particular program fragment into basic blocks, and then we have to separately see all the basic block for optimization. So input is basic block, then output is what? A DAG for block B. There is block B containing the following information. Whatever information the particular DAG has, these basic information, a label for each node, because you are drawing some particular graph. So there is a node, and that node is very significant and related with the program fragment. Definitely there is some label, means it would represent either some variable, some identifier, or some constant, or some calculation, whatever it is that. Then there are three kinds of leaves, three kinds of structure in DAG. One is root node, internal node, and leaves. So root node is called basically internal node. When internal nodes are expanded, it would reach to root node. But two kinds of node is there. One is leaf node and another one is interior node. So leaf nodes have taken raw values, whatever you are going to use for calculation, whatever values you are going to use for calculation, those particular values are directly assigned with the leaves. Then for interior node, the basic operations will be calculated by interior node. Might be some particular calculation that has been done by interior nodes, it would require further calculations. So if you are writing that particular part, suppose I have some equation, A equals to B plus C. And then again, C equals to B plus A. Okay. Then how you can put in this particular statement plus A, you are putting it is for B naught, this is for C naught. Okay. Then again C equals to B plus A. So B's value is not changed. Okay, but this C value is changed and we are putting this. So this B naught, this C naught and this C, both are different. The variable has been changed, the value has been changed. But when we are drawing this, we have to take care about the basic value because these are raw values. But this value is calculated by these raw values. So internal node, whatever put up, so that is the difference when we are using that. And the third thing is for each node a list of attached IDs, possible empty list, no constant. There is no constant. There is no raw value directly we are using. Whatever we are using, that would be represented by this variable. Means the variable particularly hold this value, that is used for further calculation. So these three kinds of particular variable will be used for generating the DAG. Now construction of DAG for basic blocks. How we can construct the particular basic block? So whatever data structure that will be used for designing this. So we need, because it is a tree structure, so there is a label, there is a left child, there is a right child, and there is a list of additional labels. Initially empty, if it is required, then we have to just associate that initial list. There are two particular functions are used for generating that directed acyclic graph. One is node ID. Whenever you are creating any particular leaf or node, we are using node ID. Initially, its value is undefined and empty. When we are just associated some value with that or any variable is associated with the node ID, then it is basically node. So return the most recent node created for ID, else return undefined, because when there is no value, it is undefined. When you are putting some value, then it is defined. Then create ID, L, R. If one node is created, definitely we need some left, some right child for that. So we have to use this particular function, create ID, L, R, and it will create a left child that is labeled with some ID and right child that is labeled with some ID. L and R are optional parameter. Why it is optional? If only left node is there, because if you are using some unary operators, definitely one node is there. There is no other node. If you are using binary operator, we will need two nodes. So that is the things. So it is optional. Might be L is there, R is there, or both are there. Okay. So that is optional. Now construction of DAGs for basic block. What kind of a statement you can convert into directed acyclic graph? So you will see that these are assignment statements. So three kinds of assignment statement will be converted into basic directed acyclic graph. So one is x equals to y operator z. That is basically complete 3 address code. Okay. Second one is for unary operator, x equals to operator y, and third one is for assignment. So whatever value is calculated and that is represented by one variable, we have to just assign that value to another variable. So three kinds of a statement, and you will see that when you are using this operator, every binary operator will be used for here. So we can change this operator for referencing any particular operator, either it is binary, or it is relational, or it is Boolean, whatever operators are there. So it has a large range of operators, and every operator will be just calculated by this directed acyclic graph. So niche in below there is an algorithm given. If ny equals to node y equals to undefined initially, then create node. If a equals to type 1, type 1, 2, 3 is given. So nz equals to node z equals to undefined. So what you have to do? You have to create their child. If it is undefined, firstly create root node, then create childs. If it is 1, if it is 2, then create only left child. If it is 3, you have to just associate one particular label with the given x. So that is given if a equals to type 1, if a equals to type 2, and if a equals to type 3. And these are very simple algorithm through which you can generate a particular DAG. Now we will just see the particular mathematical process to generate directed acyclic graph with basic blocks. So like t1 equals to 4 into I. So initially t1, because t1 is the root, So T1 is created, and T1 is created with the star variable because it is internal node. Firstly 4 is created. Okay, firstly 4 is created, then I is created, then a star is created, and we can create the all three. So that is the process. You can simply mathematically you can create, because when we are writing an algorithm like for tree algorithm, definitely you have to assign left, right child, and both the information will be updated. Initially root has some left child, so root information is updated, and left child has the root parent, then their information is updated. That's why the length of this algorithm will look like that. But when you are creating on the paper and mathematically you can design, when you are putting in system, first time you will require to place these all information in the system, but after that you will just mathematically draw that. Then again T2 equals to AT. A is what basically? A is array reference. So what we are putting? A, this array reference, then T2, then 4 into I. Again, this array reference will create it, their left child is capital, small a. So that would show the one particular one-dimensional array. Now T3 equals to 4 into I. What we are doing? We have to just add that T1 because T1 has already that value defined. So for duplicacy, what we are doing? We have to put up this additional variable into that. And then again T4 equals to B into T3. So you will see that is T4 is defined. Now T5 equals to T2 plus T4. So it is very simple thing, but I hope there is some difference. It should be like that. Plus T2 and T5. That is required. Okay. Because T2 plus T4, because T4 is right hand side, so T4 is defined like that and T2 is defined like that. Actually, this is this is commutative, so there is no problem. But still, when we are presenting in the graph, we have to give in their weightage, because if there are a lot of number of plus operators are there, then we have to follow the first plus operator will be signing that. Okay, so that order should be there, because T2 plus T4, T5, suppose we are putting here T5. So there is necessary firstly T2 plus T4 will be calculated, then the whole value will be summed up with T5. So that is very important part. Now we can go next. I equals to T5. So we have designed, this is what, this is 3 address code, or you can say that this is triples. This is kind of triples for taken from one program fragment, kind of triples, and that triples it just converted into the this. So you can say that this is the part of one basic block. Okay, so one basic block is calculated through that. Now, how we can optimize this? What are observation? Observation is a leaf node for the initial value of an ID. So you will see that for initial value 4 into I will be taken, but leaf values are associated 4 into I. A node n for each statement S. The children of node n are the last definition prior to S of the operands of n. So these are the observation. Whatever leaf node has been defined, whatever particular statement defined with the different values, and whatever childrens are defined with the particular variable. So the first particular part or first advantage of converting a basic block into directed acyclic graph is common subexpression elimination. Okay, how we can eliminate this common subexpression? In this example also given, this is another example because we are referring this example for designing the DAG. But what are the advantages of DAG? So you can see that in this example, if you are talking about common subexpression, means which particular node have more than one variable. Okay, and if we are using more than one variable for one calculation, can we take both, or both are needed, or we can just use one of them and eliminate one because both are presenting the same value. So that is the basic part. So it is called local common subexpression. So T1 and T3 will generate the same value. So we can eliminate one of them. Then again you will see that T5, I, both will generate the same value. So what we have to do? What we are doing? we are just eliminate the T5 because I is the important variable or significant variable of the program because it is used further. So T5 is temporary variable. We can eliminate that because we are using different temporary variables to facilitate the computation. Okay, that's why we may eliminate this I. So if you are seeing that advantages of this, the first is local common subexpression. How we can just finding out that you are just designing this. So we have designed this B naught. We are using the basic value B naught C naught equals to A, that is plus A, that is given. So A equals to B plus C. Then again B equals to B minus D. Which B is used? B naught, because the value of B is not updated. Minus B and D naught. Then again C equals to C plus D. So C naught is used and D naught is used and that value is C. Then again B plus C equals to E. So that is 4 variables. It would be defined by that. Now you will see that A equals to B plus C is one component, E equals to B plus C is another component. And you will see that if we are using this B plus C, the value of B which is using here and the value of B which is using here, both are different. So we cannot eliminate any of the particular expression from this part because both are looking same. These are common expressions but do not generate the same result. So that is the one part. So whenever you are going to delete common subexpression, you will see that that particular variable is another, that variable is not updated at that time, means this B plus C and this B plus C, if both have same value, then what will happen? Then this A and E that lies on the same node, but it is not happened. So you will see this diagram, there is no any common subexpression elimination. But if you are putting is that like A equals to B plus C, then B equals to B minus D, then C equals to B plus C and D equals to B minus D. Suppose if this is there, so if you're no, not it is basically you can take D equals to B minus D is okay because B is value changed. You can use that CD E equals to B minus D. Suppose we are using E equals to B minus D, C equals to B plus C. When you are going to design this B plus C, so B naught is here, C naught is here, plus is here, and A and C is on the same level. So that particular A and C is local common subexpression. So you may eliminate that. So this DAG will predict or depict the particular part where the local common subexpression has been identified by designing this diagram. So if local common subexpression is there, then you have to eliminate that. If it is not there, then there is no need for that. So this is the important advantage of this particular part. Now second one is dead code elimination. So if you are talking about dead code elimination, when you are going to design the DAG, you will find that during DAG designation, some of the statement will left. Means that particular statement will not placing in the designed directed acyclic graph. So if those particular are codes which is not placed in the DAG, that is called dead code. Okay, like that. In particular, this program, this particular diagram, A equals to B0, C0, B equals to A minus D, that will be given. Then D equals to again A minus D. C equals to D plus C. So you will see that B and D both are local common subexpression. So the converted, the particular part is showing that these three statements, because B and D both represent the same thing. So this shows B is not live. Why it is not live? Because it is basically problem of local common subexpression. But if you are talking about dead code elimination, so like we can write this. If debug, suppose there is a code and debug equals to false. Suppose if debug equals to false. Okay, so if debug equals to false, if it is false, then there is no need for this condition. So that is called dead code elimination. So this is the complete advantages of directed acyclic graph. So we will discuss another particular kind of optimization in next lectures. Thank you very much.